So today we're going to finish up on 7.2, okay, part 2, and we'll wrap up kind of what we're going to be doing with inverse trig functions, and then tomorrow and Wednesday we're going to talk more about tomorrow and Thursday. We'll talk more about regular trig functions. Okay, so this will kind of wrap up what we do with inverse. And what we're going to try to do in this section is take a formula that has trig in it and convert it to an algebraic equation. So a formula that has trig means it has a function like sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent, secant. It's got something like that. We want to see, is there a way we can get rid of the trig part of it and just turn it into algebra. So algebraic expressions can have addition, subtraction, multiplication, division, variables, squaring, square rooting, anything like that. But you can't have sine, cosine, or any of that stuff in an algebraic expression. That makes it a trig expression. So we're going to see if we can convert trig just to algebra. Right? And you can't always do that super easy, but the kind of problems I give you today, there's going to be a trick to get that done. So what we're going to be looking at, let me just show you an example of a problem, and then I'll give you the directions. You're going to have two trig functions. A lot of times you'll have like a regular one on the outside and an inverse on the inside. Not always, but a lot of the time. And the key is going to be to start with this inner trig function and do something with that and then make a diagram. So we're going to start with the inner trig function and we're going to set up a diagram. Because whenever you're doing inverse trig, you're solving for an angle. If you're solving for an angle, then you could draw a diagram about that problem. And that's what we want to do first. If the inner trig function is inverse, okay, if you have an inverse trig function on the inside, then it's going to help to rewrite that as regular trig. And that's exactly what I did in one of the homework questions to try to figure out what Tim had asked. So we can take a inverse trig function and we can reword it. And by doing that, that actually helps you to make the diagram anyway. A couple things to keep in mind as we do this. Pythagorean theorem is something that will come up. I think that's all you really need to worry about. Keep the Pythagorean theorem in mind. And the way that's going to usually come up is we're going to figure out two sides of a triangle, and then we're going to need to know the third. It's going to be a lot of variables, so we're going to have to be pretty good at using Pythagorean theorem with all variables. Okay, and that's our first example. So it says to write an algebraic expression in terms of v. V just happens to be the variable that I picked. The name of the letter doesn't matter. It could be x, could be n, that doesn't matter. All right, so when we're done, we're going to put our answer in that box. So let's go back and look at the directions. It says start with the inner trig function. And specifically, if the inner trig function is inverse trig, we're going to rewrite it, okay, using regular trig. So in this case, is the inner trig function inverse trig? Yeah. So let's start with now. We're going to forget about that we have this sign on the outside. We're not even going to come back to that till the end. We're going to focus on this. The inverse cosine of v. Now, we know that this is always going to give us what kind of answer? whenever you use inverse trig, you're trying to solve for what? Yep.
An angle.
An angle, exactly. I don't know what that angle is going to be. But when I'm done, I'm going to have an angle inside those parentheses. Okay? So let's just say inverse cosine is going to equal an angle. It's going to equal some angle. And I just used a Greek letter to represent it. Now what I'd like to do is rewrite that equation in terms of a regular trig. So what could I do to both sides to get rid of inverse cosine? Yep. Michael?
Take the cosine of each side?
Yes, take the cosine. So remember, functions, you can't add, subtract, multiply, or divide with them. You can only take the function of both sides. So when I do this, there's absolutely no multiplication happening at all there. I'm taking the inverse cosine of v, and I'm plugging that into the cosine function, okay? And I should have left a little space. Let's do the same thing here. Again, there's no multiplication there at all. We're taking the theta, and we're plugging it into the cosine function. Now, when you do that on the left, it's going to cancel. Cosine and inverse cosine will cancel each other out. Now, we have this. V, the cosine of theta, equals V. Well, I can draw a sketch of that. So we're going to make a right triangle. And we have to make a diagram that lines up with what we just wrote. Put theta anywhere you want. Not the right angle, but any one of the acute angles. Now, if you take cosine, does anybody remember what the definition of cosine is? Yep.
Adjacent over hypotenuse?
Correct. So somehow, if you take the cosine of theta, it has to come out to v. That's what this equation says. We know the two sides that are going to be involved. Nick just said it was adjacent and hypotenuse. So can anybody tell me what I could label the adjacent side as and what I could label the hypotenuse as, so that if I take the cosine, it comes out to v? Yep.
You could label the hypotenuse 2v and then the adjacent 2.
Okay, so you could do that. How about even simpler? But that's exactly the right idea. Yep.
You can do one B.
Okay, wait, how about this side? What do you want to make it?
One.
One, okay.
And the hypotenuse B.
So that would give you adjacent over hypotenuse. That says the cosine is 1 over v.
Flip them around.
Yeah, we gotta flip them around. So we want the adjacent to be v, and we want the hypotenuse to be 1. Now the cosine is adjacent over hypotenuse, and that picture matches up with that equation. Questions on that? Now let's go back up. What they really want to know in this problem is the sine of theta. Well, here's theta. What's the definition of sine? Yep, Matt? Opposite over hypotenuse. Well, the problem is I don't know opposite right now, but I do know the other two sides. So how can I figure out the opposite? Yep. We can use Pythagorean theorem. If you want to temporarily call it a variable, you can. We're going to cross this out in a second, but we could call it x. And now let's set up Pythagorean theorem. X squared plus v squared equals 1 squared, and now solve for x. There you go. It's the square root of 1 minus v squared. Any questions on that? All right, so let's put that here. Now we can do what they want us to do. Find the sine. Sine is opposite over hypotenuse. So the square root of 1 minus v squared divided by, in this case the hypotenuse is just a 1, so we don't have to worry about it. So that is your answer. The sine of the inverse cosine could be calculated by just doing the square root of 1 minus v squared. Now I could check that with a single value and make sure it works. But how could I check it on a graphing calculator? What's something I could do to confirm those two things are exactly the same? Yeah.
Graph each of them.
Yeah, let's graph each of them. And if they're the same, then they should line up exactly, right on top of each other. So we got the sine, let's clear that. The sine of the inverse cosine of x, and then we're going to put in the square root of 1 minus x squared. All right, I'm going to do zoom 7. I think that'll probably be good enough. Let me double check and type that in right.
I don't think you've made it inverse cosine.
Yeah, I knew something was weird. Okay, so sine of the inverse cosine of x. Now let's do a zoom 7. Maybe that was hard to see, so let me zoom in. Zoom. I wanted to zoom in so you could see it better, but it... Oh, maybe I can now. Oh, I can't zoom in. All right, I'll do it by hand. So let's go -3 to 3. And I'm just going to do -3 to 3. So there's the way we're doing it on the left. And there's the formula on the right. What do you notice about the speed, too, when you graphed it? Anybody notice that? So let me, if I just type it in again, I think it'll do it over. Okay, watch the first one. And the second one. What do you notice? Yep.
The second one's a lot faster.
Yeah, the second one's faster. So not that that's really important for us, but the point here is, if you were going to use this in some type of formula in a computer, if you can do it faster, that's better. Right? So this is actually a much less computationally intensive formula for a computer to deal with than this entire thing. Right? And it shows they're exactly the same thing. So that's how you can convert a formula with trig to a formula that has no trig in it at all. Any questions on that? I'm going to try another one. Okay, we'll even do one with a specific value. That's even easier if you actually had a number for v. But that's the general idea. All right, let's try this one. The tangent of the inverse sine of v. I want to figure out what that's going to equal. All right, so what's the first thing I do with inverse sine of v? What am I going to set that equal to? So,
Theta.
yep, I'm going to set that equal to theta, and then that just means that when we do that problem out, we're going to get some kind of angle. So if the inverse sine of v equals theta, can somebody tell me what that would mean when you get v by itself? John?
V is equal to sine theta.
V is equal to the sine of theta. All right, so now I want to draw a diagram. Put theta in it. And based on the equation that's right above it, what two sides do I need to label? Sophie?
Opposite and hypotenuse.
I need to label the opposite and the hypotenuse. And when I label the opposite and the hypotenuse, the opposite divided by the hypotenuse has to come out to v. So how would I label the two sides? Again, there's an infinite amount of ways to label them. I try to use a 1 in there somewhere to make it easier. Yeah? Yeah.
V is the opposite and 1 is the hypotenuse.
Yep. So now when you do the sine of theta, you get the opposite divided by the hypotenuse is equal to v. Now, what do they really want? They want the tangent of this. Remember, this is theta. So they want the tangent of that. Tangent is opposite over adjacent, so I need this other side. Let's temporarily call it x. Can anybody set up my Pythagorean theorem for me with the information I have right there?
V squared plus x squared equals 1 squared.
B squared plus x squared equals 1 squared. This looks very similar to the last problem. In fact, it's the same thing. So when you solve and get x by itself here, you're going to get the square root, 1 minus v squared. That comes up a lot. And now they want the tangent. Well, tangent is opposite over adjacent. So that's v divided by the square root of 1 minus v squared. But we have a problem now. This didn't happen in the last one, but it did happen here. What's the problem with that? Nick?
There's a square root on the bottom.
Yeah, we can't leave that square root on the bottom. So how would you fix that? John?
You would square both sides, but then you have a higher power on the bottom and you on the bottom.
So I don't have sides here, I just have a single expression. So there's nothing here that I can square without messing up. There's only one thing, you want to multiply, but there's only one thing you can multiply a fraction by.
Yeah, you would multiply both like halves by the square root of 1 minus v squared.
Yep, multiply the top and the bottom by the same thing. And what that does is it gives you the square root of 1 minus v squared squared. So it squares the whole numerator, or denominator, and it gets rid of that square root. Now in the numerator, you have v times the square root of 1 minus v squared. And that is the final answer. V times the square root of 1 minus v squared over 1 minus v squared. Okay. Questions on that? Okay. That's kind of the same thing. Does anyone want to see a third one of that type? It's the inverse on the inside, regular on the outside. It would be pretty much the same. Okay, yep, this is different. So this says to evaluate without a calculator. That means that it has to come out to a nice answer. It also means that it's going to rely on things that you've learned in the past or memorized, like special situations. So, we're going to evaluate this. Let's start with the inside and see if we can figure that out. This is just the tangent of an angle. So this goes back to unit circle trig. We just have to figure out if it's a 45, 45, 90 or a 30, 60, 90. But it's going to have to be one of those. Otherwise, you can't do it without a calculator. All right, so let's start with 3 pi over 4. I'm doing this one totally different because it's not inverse on the inside. Okay. I'm actually going to figure this out. What's 3 pi over 4 in degrees? Nick?
45.
Pi over 4 is 45.
So 180.
That's pi. Yep.
135.
135. So what I want to do now is on a unit circle, I want to draw a 135 degree angle and figure out the tangent of it. Okay, where's 135? Huh?
It's halfway between 90 and 180.
Right, it's exactly halfway between 90 and 180. So is 135 a multiple of 30, or is it a multiple of 45? So
45.
it's a multiple of 45. So that means this is a 45, 45, 90 right triangle. In a unit circle, we know the hypotenuse is 1. That doesn't help at all. We need the other two sides. How long is each leg of a 45, 45, 90 triangle in a unit circle? Has a square root in it. Yep.
Square root of 2.
Yep. Oh, that's part of it. Square root of 2. John?
Is it 2 square root of 2?
No. Yep.
Square root 2 over 2.
Square root of 2 over 2. So each side is square root of 2 over 2. Now we're looking for the tangent. If you remember the formula for tangent, you could think of theta as right here. It's opposite over adjacent. Well, you know the opposite, you know the adjacent. You could also think of it as y over x. Same thing. Now we have to be careful because this is in quadrant 2. So if we were to write this 135 degrees as a coordinate, what would the x value be? Yep.
Negative square
And the y value?
square root over 2.
And the tangent is y over x. So what do you get when you divide y by x, or opposite over adjacent in this case? John?
You get negative square root of 2 over 2 over square root of 2 over 2.
Mm-hmm. And what is that?
Simplifies it. That'd be like 2 times square root of 2 over 2 over square root of 2. And then you have to multiply both sides by square root of 2.
Possibly, I'm not sure. Tim?
Negative 1.
Negative 1.
Oh.
Because you're dividing two things that are opposites. So if you're going to divide opposites, the answer is always negative 1. So now we know what this whole thing is. We just simplified it. So now this problem really turns into this. I want to know the inverse sine of negative 1. Well, whenever we do inverse trig, what kind of answer do we always get? Now this is kind of going back to what I just showed you. Nick?
Angle.
You're going to get an angle. So I'm looking for you to tell me an angle. That's the answer to this problem. How could I rewrite this without inverse trig? Yep.
Take the sine of each side.
Take the sine of each side. So what I'm asking you, if you want to think of it this way, is what angle can you take the sine of? And the answer comes out to negative 1. Well, we know negative 1 is the low point in the cycle. So think of what the graph of sine looks like.
Pi.
1, negative 1. So here are your points. These are all marking the quarter points. So I basically want to know what's the x value right there. That's the answer. What angle can you take the sine of? And the answer will come out to negative 1. Yep.
360 degrees.
360 would be right here.
Oh, 270.
270 degrees. Yep. Or what is that in radians?
3 pi.
3 pi over 2. Yep. So a lot of nice things had to happen to make that work out, so we could think it through like that. Okay. If we had a number here that was like 0.7, there's no way you're going to figure out what angle you could take the sine of and get 0.7 as an answer. Not without a calculator. Okay? So in this case, I'm not really that interested in the fact that you could get the answer. I mean, you could just type it in on the calculator. I'm more interested, could you think through the unit circle, figure out the inner function based on a unit circle, and then deal with the outer function by thinking about a sketch. Or maybe you could think of it a different way, but I think of it as a sketch. Right, so that's really a good problem to kind of tie together lots of things we learn and make different connections between stuff and trig. Any questions on that one? Okay. All right, let's do this. Now, this is back to the first types of problems we were doing. Regular on the outside, inverse on the inside, but now it's going to be even easier because you have numbers. So your final answer will be a number. You're not going to have like the square root of 1 minus v squared over v or something. You're going to have all numbers. Okay. So, what's the first thing I should do? John?
Set it equal to an angle.
Say it again.
Set it equal to an angle.
Set what equal to an angle?
The argument like sine of, or sorry, opposite sine of 1/2.
So take the inverse sine of 1/2, set that equal to an angle, because we know it's going to come out to some angle. Okay, now what would I do with that? Yep.
Take sine on both sides.
Take the sine on both sides, so we can rewrite it with regular trig, which then allows us to do the next step. So we know 1/2 equals the sine of theta. And now, how do we want to represent that equation in a different way? What do we want to do? Yep.
You draw a right triangle.
Draw a right triangle and put theta in it. And what's the definition of sine? Yep.
Opposite over hypotenuse.
Opposite over hypotenuse. So I know my opposite is 1 and my hypotenuse is 2. What's my adjacent have to be if I use Pythagorean theorem? No decimals. Yeah.
Square root 2?
Square root of 3.
Oh, yeah.
Square this, you get 3. Square this, you get 1. 3 plus 1 is 4. And the square root of 4 is 2. Now we've got all our sides. And we're good. And you should actually recognize that as a special right triangle. That's from the homework. 1, 2, square root of 3. So if you recognize that, you really, at this point, you almost know the answer. But let's just finish it off. So they want the cosine of the diagram. What's the cosine in this case? Square root of 3 over 2. And that's your final answer. So technically, even though I said you should know what that angle is, you don't have to. Because I never wrote down what that angle is. It's a 30-degree angle. But you didn't have to actually find that to do this problem. Because they didn't want to know the angle, they wanted to know the cosine of the angle. Questions on that? All right. Let's see. 2 left. So this part, a little bit of a review, but they put it in here, so we'll just mention it again. But remember, when you're solving a trig equation, you can get many solutions to a problem. Right? So if you had like a wave, like sine of x, and it said sine of x equals 0.5. Put a line in at 0.5. It's going to hit it infinitely many times. So if there's one solution, there's infinitely many. Now, how often do solutions repeat themselves in a trig function? I'm not even thinking of a number, I'm thinking of something more general. They repeat every cycle. So you have to figure out what the cycle is of your trig function for sine, cosine, secant, and cosecant. The period formula is 2 pi over b. For tangent and cotangent, anybody remember what the formula is for tangent and cotangent to find the cycle length? Yep. Pi over b. And remember, b is the number in front of x. It's the same b, it's the notation I always use when we talk about transformations. The number, it's the coefficient of x. All right. So remember, the idea is to use find one solution and then put plus the period times n. That means that the solution can repeat every single cycle. If you're going to use a calculator to type these in and solve it, remember you may have to use a reciprocal identity, because if we had secant, cosecant, or cotangent, we don't have buttons for those. So we'd have to type them in as 1 over sine, 1 over cosine, or 1 over tangent. Now, all of this stuff, this period stuff, is only if they ask for all solutions. If they give you a problem and they specifically say, find solutions between 0 and pi, well, then that's all you have to do. Set your window to 0 to pi and write down all the answers. If they say all solutions, then you do plus the period times n. Okay? So you just read the directions and see what they say. All right, so this says find all solutions. So the first step, find all the solutions in one cycle. So let's start by finding the length of cycle. I'm dealing with sine. What's the formula to find the period of a sine function? John?
2 pi over b.
2 pi over b. In this case, what's my b value? 1. So the cycle length here is 2 pi. So that means once you find a solution, if you add 2 pi to that solution, you'll get when it occurs the next time. And if you add 2 pi again, you'll get the next one. Okay, so we know that our cycle length is 2 pi. That also helps us set the window. We don't want to look at more than one window or more than one cycle. Just focus on one cycle. That means you need to set your window to a width of 2 pi. There's lots of ways to do that. There's tons of ways. What's the easiest way to set an x width of 2 pi units? John?
From 0 to 2 pi.
I would just go 0 to 2 pi. You could go negative pi to pi. You could go 1 pi to 3 pi. It's kind of weird, but you could. I would just do 0 to 2 pi. Y min and max, as long as you cover the range, you're all set. And the range of sine is -1 to 1. So that's fine. Windows setup. That's probably the harder part. Now the easy part, just type it in. One thing I should have checked first, but I got lucky because my last problem was in radians. I should have checked my mode to make sure I was in radians, because this cycle length was in radians. What if they wanted it in degrees? What's 2 pi equivalent to in degrees? Yep, 360. I could have done 0 to 360. All right, so how many solutions am I going to get per cycle? Okay.
2.
2. So I need to find both of them. We'll call them x1 and x2. I already know how often they're going to repeat. They're going to repeat every 2 pi units. So you can put plus 2 pi n and 2 pi n. Quick reminder, what's n again? N is a, yep,
Number of cycles.
the number of cycles, and it has to be what type of number?
A whole.
It can be a little more than just a whole number. It has to be, yep.
Real. I don't know.
No, it can't be real, because real would include fractions and decimals.
Rational.
Radians.
Rational would still include fractions. Yep.
Integer.
Integer. Has to be an integer. You can only add a whole cycle. You can't say that this answer is going to repeat again half a cycle later. No. It's only going to repeat 1 full cycle later or 2 full cycles later. There's nothing in between. Okay. So n stands for some integer. So, what do I have to do now? Find the intersect. Second calc intersect. If you just hit enter 3 times, it'll randomly find something. So I got that one, 2.498. Doesn't really matter if you call it x1 or x2. And second calc intersect. Now I do need to be a little bit more careful. That should be fine. 0.644. And that's how you write your solutions.
Mr. Hager,
Yes.
So how'd you get B again, and what was it?
B is the coefficient of x, which in this case is just a 1.
Oh, okay.
So B is always given to you. Okay, any question on that one?
How did you get 2 pi on again?
How did I get 2 pi?
Yeah.
That's just the formula
Okay.
for sine, cosine,
I know.
secant, and cosecant. Just the formula.
Okay.
This one, the last one we do, this one has a different formula. Cotangent equals 2.5. What's the formula to find the period for a cotangent function? Yep,
Pi over b.
pi over b. Cotangent naturally cycles faster. Pi over b. In this case, b again is a 1. So our period is pi. All right, so now what we want to do is, if I leave my window like that, I'm going to see 2 cycles of cotangent. Don't need to look at 2 cycles. All I need to see is 1 cycle, because beyond that, it's just going to be a repeat. So let's just go 0 to pi. Now, if you're not sure, we can always just hit graph and check it, but does anybody remember what the range is on cotangent? It's the same as the range on tangent, or the domain of inverse tangent. Yep.
Negative infinity.
It's negative infinity to infinity, so it's going to go up and down forever. As long as you basically cover what number they want it to equal, and that's in the window, you're fine. So technically negative 3 to 3, 2.5 will work. Okay, that's going to be fine. Let's put in cotangent. How am I going to type cotangent in? Nick?
1 divided by tangent.
Yep, 1 divided by tangent. Do not use second tangent. That has nothing to do with cotangent. That's inverse tangent. Totally different. So 1 divided by tangent. Put in 2.5. Hit graph. You're going to see exactly 1 cycle. It's got that curved shape to it, with asymptotes on the left and the right edge of the screen. Okay, how many answers per cycle here? Yep,
1.
just 1. So second calc intersect, you should just be able to hit it 3 times. You should just find it. Perfect. Okay, can someone tell me how I'm going to write that answer? So
0.38 plus pi.
pi, yes. So that means you can add or subtract 3.14 to that number as many times as you want, and it'll give you an answer somewhere else. That's it. Any questions on that? Okay, we got a lot of time today. We usually don't have that much time. So let me put up the homework, and then we got about 20 minutes. Okay, so 394. It's not that many, 37, 38, 41, 42, and 44 to 53. So tomorrow we'll do 7-3, and then Thursday the plan will be to do 7-4, and we'll have our first test for term 3 on Friday. And I'll let you know for sure about a reference sheet on this one by tomorrow. I think. In fact, I can tell you right now. Yeah, you can have a reference sheet for this one. It doesn't mean we're going to do it for all of them, but this one you can.